In this video, we're going to review a couple of the concepts about vectors that we've already seen and then start talking about dot product. So, finding the unit vector. If you'll recall, a unit vector, the first thing we need to do is find the magnitude of our existing vectors. So we do that by using kind of a modified Pythagorean theorem. We've got -2 squared, 3 squared, and 5 squared. So 4 plus 9 is 13, plus 25 is 38. So this is the square root of 38. So this is a scalar that we modify our original vector by. So it's -2 over the square root of 38i plus 3 over the square root of 38j and plus 5 over the square root of 38k, if I can kind of fit that in. Okay. Next, finding the angle between the vector 5a plus j and the x-axis. So let's talk about how we would do that. We would go over 5, up 1, so this is that vector. So of course, kind of making a triangle out of this. To find that angle, we would simply use inverse tangent. So the angle would be equal to the inverse tangent of opposite over adjacent. So we could type that into our calculator, and that would be it. Joe Mauer connects with a baseball. I'm being, of course, a little funny here in that the ball is only leaving with a speed of 75 miles an hour at an angle of 5 degrees. So it's definitely not a connection in that this is not heading out of the ballpark. Find the vertical and horizontal components. So if you'll recall from the work we've done, we say, okay, so the speed is our hypotenuse. This is the speed off the bat. It is coming at only 5 degrees. So to get the horizontal component, we would use cosine. And to get the vertical component, we would use sine. And again, the reason for that is because here, this is the adjacent side, adjacent to the angle. So that's why it's cosine. And this is the opposite of the angle, and that's why we would use sine. So let me kind of color coordinate this. We would do 75 multiplied by the cosine of 5. That would give us the horizontal. And the vertical would be 75 multiplied by the sine of 5. And really, again, the reason for that is if you think about, the cosine of the angle is equal to the adjacent divided by the hypotenuse, and we would multiply both sides by 75. And we looked at that previously, but again, just for a reminder, there's the reasoning. So we're going to begin talking about dot product today. And dot product is actually a pretty easy calculation. There's just a couple of things to kind of think about with dot product coming up. The dot product of two vectors, a dot b, is simply the x component of a multiplied by the x component of b, the y component of a multiplied by the y component of b, and then added together. So it's the sum of the x product and the y product. That's one formula. Another formula is to say if I dot two things, that's the same as the length of A times the length of B times the cosine of the angle between them. There are a couple important things here, and I want to talk about the formula, but one important thing is to recognize that the dot product will, when you calculate it, will give you a scalar, just a number value. It's not going to give you a new vector. It's going to give you a scalar. And if you recall, a scalar is like something you put outside a vector that multiplies it, that extends that original vector. And that's important here because I want you to think about a dot product as really being what effect does this B vector have on this vector? How much does it strengthen it or extend it or scale it? Okay? How much does the second vector affect the first vector? That's really what we're talking about, and it's a number. It's one number. The dot product kicks out a number. Something we'll talk about in the coming days is a cross product, and that returns a new vector. So vectors have two products at work. Okay. Now, the first I kind of did this in reverse order. The formula that deals with cosine really is saying how does, we've got this vector here, B, and it's saying how would vector A affect it if you did B dot A? Well, really we want to know how much of an extra push along B A provides. So you can see there's kind of a rotation of the baseline to say, well, okay, we have an angle, and if I just figure out how is this red vector affecting the blue, I could figure that out by figuring out the cosine, using cosine to figure out this adjacent side to figure out how much is the red helping the blue along. Okay, so you say, well, magnitude of A, of course, is the hypotenuse multiplied by cosine of the angle. This is similar to the Joe Mauer problem we just did, multiplied by the length of B. And this, of course, is that second formula. And again, it comes back to what I said. It's giving us a scalar that says how much is the red helping the blue along or pushing the blue along or giving it an extra boost. I'll come back to that in a second. But let me move this second one in. Move that out. So the second formula is kind of the one that's more, that we use more often. This is that kind of, figure out the x components, figure out the y components. So you can see here, I've broken each vector kind of into pieces, and I've said, okay, vector A has a horizontal, vector B has a horizontal, and I combined them. I multiplied those two together, and I said, how do the horizontals work with one another? And of course, the same thing. The vertical components will work together. Here they are. And my assumption, or the work here says, I'm really not considering how the horizontal of A and vertical of B, or how the vertical of A and the horizontal of B work on each other, because they aren't helping each other. Okay? Those things are not helping one another. They are perpendicular to one another. So it's the horizontals and it's the verticals, and we really we don't think about how they affect each other in the opposite direction. A way I saw this presented years ago had to do with Mario Kart. Okay? And it really, if you've ever played the game, you've got a red vector, it's the way you're going, and the question is, if I hit one of these power pads, what happens? If you hit it straight on, of course, it just shoots you off in that direction because both vectors are working together. Okay? If you hit it at an angle, you kind of get pushed, and you'll keep going in your direction, but you'll be pushed a little to the side, but you'll continue in your direction. And if you hit it at completely the opposite, you're not going to get any boost at all. And that is kind of what the idea of a dot product is. It's how much, quote unquote, boost you're getting. If you hit it at exactly the same as, that both vectors are the same, you get a huge boost. If you hit a little off, you'll still get a boost, but not as much. And if you hit it at a perpendicular, you're really not going to get anything out of that power pad from Mario Kart. And this is the idea of the dot product. That boost is the scalar that says how much does that original vector get pushed. So we've got some geometry or some geometric interpretations. When you add vectors together, you accumulate two vectors. You go one and then the other, and that resultant vector is like that. If you multiply by a constant, you just keep extending your original vector along. The dot product is how is one vector applied to another. How much stronger have you made the original vector by applying the second one? So you have three results that can happen. 0, meaning kind of that what we had talked about with that boost on Mario Kart, you get nothing out of it. A positive means you grew in the original direction. Your original vector was pushed still in that direction. Negative means you're actually growing in the opposite direction. All right? Let's calculate a little bit.